With Lecture 12.1, we're starting with Chapter 5 to discuss two different kinds of equilibrium constants, Kp and Kc. So when we think about equilibrium, if we start a reaction with all N2O4, the concentration of that is going to drop over time. And initially, we won't have any of the product, NO2, and the concentration of that is going to increase over time. But at a certain point, the concentrations don't change. That's when we have reached equilibrium. We'll be talking about rate laws in Chapter 10. For now, I can tell you that equilibrium is also reached when the forward rate is equal to the reverse rate. Once those two rates, forward and reverse, are equal, the concentrations don't change. Thus far, in Chapter 4, we talked about the relationship between delta G naught at standard state and equilibrium. This equilibrium constant has to have the materials in the standard state. So that means all gases are at 1 atmosphere at standard state, and all solutions are at 1 molar concentration. But of course, when we get delta G naught from K, we're taking the natural log of the equilibrium constant. You can't take the natural log of units. So what we do when we're dealing with free energy is to take our pressures and divide them by 1 atmosphere, and our concentrations and divide them by 1 molar, so that our equilibrium constant is unitless. But now that we're in Chapter 5, we're going to be using equilibrium constants not in the context of free energy, but with the idea of getting concentrations of things in solution or in the gas phase. So if we are working with an equilibrium constant in which all the materials of interest are dissolved in something, we usually work in units of molar. So we call this kind of equilibrium constant K subscript C to indicate that we're dealing with aqueous or dissolved materials in solution. So of course we leave out the water because that's in the liquid phase, and this equilibrium constant has units. For this particular reaction, we have the bromate times the hydronium over the bromic acid. Each one of these materials has their concentration in molar, so if I have molar squared over molar, of course, the one on the bottom cancels out with one on the top, and the overall units of my equilibrium constant here are units of molar. Sometimes you might be working where all your materials are in the gas phase, so we use subscript P to indicate that we're talking about an equilibrium constant where we are measuring the concentrations of things in atmospheres. So as all these materials are in the gas phase, you notice we have the pressure of water in atmospheres squared because of the 2 in front of the H2O over the pressure of H2 in atmospheres squared and the pressure of oxygen in atmospheres. And once again, you notice this equilibrium constant, Kp, has units. The atmosphered squares cancel out, and we're left with just 1 atmosphere on the bottom, which makes our units for this equilibrium constant atmospheres to the -1. Now, sometimes you're in a situation where your analytical data for your gas phase reaction is in molar, but if you're going to use gas phase reaction data to get free energy, you're going to have to convert your information that is given to you in concentration to information in pressure, so you can use the right units to get delta G naught. How do we do that? Well, let's look at our friendly ideal gas law equation, PIVNERT. If I take the volume and move it to the other side, I have a relationship between pressure and, of course, moles over volume is molarity. So I have a conversion factor from getting from pressure to molarity, or Kp to Kc. And the formula is this. If you need to get Kp, it's equal to Kc times RT delta Ng. T is going to be in Kelvin. Delta Ng is what we did when we were calculating for work. It is the moles of gas in the products minus the moles of gas in the reactants. Our R constant is going to have the value 0.0821 atmosphere per Kelvin molar. We do that so that we can take our Kc units, which are in molar, and get them to cancel out. And of course, Kelvin cancels out, and we'll be left with Kp units of atmospheres. So here is your question. Determine Kc for the following reaction given that Kp is equal to 1.48 times 10 to the fourth atmospheres to the minus 1 at 298 Kelvin. So first, the formula I gave you, Kp equal Kc times RT to the delta Ng, isn't quite the right direction that I want to go. So let me rearrange it. When I rearrange the math, I get Kc is equal to Kp times RT raised to the minus delta Ng. So to get delta Ng, I have 2 moles of product gas and 3 moles of reactant gas. So my value for delta Ng is going to be minus 1. Now let me substitute what I know into the formula. So I'm going to have 1.48 times 10 to the fourth divided by atmospheres times the quantity 0.0821 atmosphere per molar Kelvin times 298 Kelvin to the minus 1. So something to the minus 1 is actually something to the first power. So hopefully you notice that our units cancel out very nicely so that whatever value you get will be in units of molar to the minus 1. And that should make sense to go from atmospheres to the minus 1 to molar to the minus 1. And that's how you do that kind of problem.